among 2 or more classes based on a bunch of features, typically image features or object features, and machine learning methods as applied to image analysis. In the situation where the images come from ordinary cameras, whether video or still cameras, the analysis from those is called computer vision. That course is offered once per year in the normal schedule. It's a little bit up in the air what's going to be, when it's going to be offered next year. The reason being, as of this past fall, we had just one professor who specialized in computer vision, and he was in his early days as a professor, and for professors in their early years, we accommodate them by having them teach only in the very subspecialty areas that they're in, so that they can try to attract research students. So he has not been teaching the computer vision general course, and I don't think he's scheduled to do so next year either. We just hired, excited to say, a new, so the present computer vision professor is named Geddes Bertasius. We just hired a brand new, wonderful young professor named Somyadip Sengupta. He's a computer vision person. And it's possible that we will, between now and the fall, hire a senior computer vision professor. So we have traditionally had a lot of strength in computer vision. Computer vision is applicable, of course, to, for example, automatic driving is a very common application these days. But there are serious medical applications as well. In fact, a research team that I'm leading is focused on helping alert colonoscopists to parts of the colon, the large intestine, that they didn't survey, that they never looked at. Somehow they didn't point the camera at the whole colon, and to do so in real time. And that's a computer vision objective. Anyway, the point is that we do offer regularly a first course in computer vision, and you should be aware that that may be of interest to you given the background that you have here in this course. I'm at the end of my teaching career. This is going to be the last time I offer this course. And no one else has offered it yet, since I started it. And I have no reason to believe that it will continue to be taught. We have recorded the lectures of this. They're all going to be in public on YouTube. And if you want to go back to any of the lectures, you can. And they're on Panopto this semester also, but not everybody has availability, can get to the Panopto site. But they are and will be publicly available. And so if you have colleagues, fellow students, or faculty who want to learn the material in this course, they can go to those YouTube lectures. In fact, there was a failure in recording for 2 of the lectures, and we went so far as Mike and I showed up one evening or weekend and completely redid the lecture so it would be recorded in the series. So it's also the case that 775, it's going to be offered every fall, even though I'll not be offering it after next fall. But I have in past, every 2 years, offered a course on shape, on object shape, on essentially a combination of mostly differential geometry for users, if you will. And that's not going to be offered anymore, but it's available by recording as well. Okay, so for people who want that. Professor Mark Needhammer offers periodically a course called Comp 777, which is about optimization in image analysis. So if you take 775, you will find that a whole lot of the methods involve coming up with some objective function that you want to achieve. For example, in segmentation, the most probable geometric description of the object given the image. So you have this probability function, and you want the optimum overall possible object descriptions. Well, the methods for achieving that are important. Likewise, registration turns out to be typically an optimization problem. The first order machine learners are doing optimization, right? These deep learning methods have so-called loss functions, which are the opposite of rewards, penalties, and you're trying to minimize the penalties, and these machines are designed to try to produce these minima. And so these methods for optimization are very broadly used, and Mark Needhammer offers a very useful course in that area. Next spring, I will be teaching a special topics course on object representations and statistics on object representations. So, for example, doing diagnoses based on shape properties, right? Diseases tend to make certain structures in the body misshapen, and you can use the shape to help you decide whether a patient's diseased or not. Okay, so these are all courses that you, in principle, given that you have taken this course, may be interested in and you're well prepared to take. Any questions about anything in courses going on? Okay, so with that, today's class is dedicated to questions on any course material at all, and that includes things that came up in the practice final. So I'll just open the floor for questions. Yes?
Could you go over the difference between the computationally useful and necessary Gaussian aperture features?
Computational usefulness versus what's necessary?
Yeah, because there was a question on the last midterm where it was saying which aspects of the Gaussian aperture made it were necessary for it to be the best aperture.
Okay. First of all, many of the methods we talked about in the course really divided themselves into two types. One was transformations on images. So you have an image in, and you're trying to get edge strength out, or bar strength out, or how like it is to some particular model, for example, by so-called match filtering, or Anyway, these are transformations on the images to produce images. And we talked about those in two classes. At a single spatial scale. And multi-scale. The other class of methods we talked about were transformations, let's say geometric transformations on space. Okay? And we needed those for rotating images and translating them and scaling them and deforming them for registration purposes, for example. In regard to these guys, many of the operations that we wanted to do were linear and shift invariant. That is to say, they can be understood as convolutions. What's necessary, if you will, if you're trying to get edge strength, is, for example, taking a gradient by using derivatives of a Gaussian operations. But you can do that in many ways, and in particular, as long as the convolution kernel is more than a little bit, is bigger than something really quite small, you benefit efficiency-wise by doing it in the frequency domain. That is to say, by applying the FFT and then doing multiplication in the frequency domain, and then taking the inverse. Doing it for that reason takes advantage of the fact that the eigenvectors, the eigenimages of shift invariant operators are the sinusoidal pairs, right? The sines and cosines at a given frequency. Remember that it is a pair. Anyway, the point is that doing a convolution at all to get a derivative of Gaussian applied is a very good way, effective way to get edge strength. Doing it by the frequency domain is not necessary for effectiveness, it's only efficient, right? Realize that there are sometimes operators on images that are linear but not shift invariant, and then you don't have available this efficient approach of going via the frequency domain. And for those who have understood, if you have two places in the image and you think of the output at this place as a linear combination of pixels here, and I guess everybody must know by now that this weighting function is the reflection of the kernel. in a shift invariant situation, the kernel that's used down here is the same as the one here, except it's just shifted over to be centered at a new place. But for linear non-shift invariant, it's still got a kernel, but the kernel changes as you move around the image. Right? The kernel that you use over here is a different kernel from the one you use over here. Okay? And that may be because there's some special knowledge about what has to happen over here different from what has to happen over here, in which case you still can carry out the operation, but not via the frequency domain. Over here in the geometric transformations, we had 3 different ways for understanding, or 4 actually, different ways for carrying out rotations. Who can name the 4 ways? Someone name the first way.
Quaternions.
Quaternions the same way, right. What's another way to do a rotation?
Euler axes.
Yeah, okay, so Euler angles. Euler angles.
Rotation matrices. Rotation matrices.
Rotation matrices, right? And I will note that there are 2 kinds of ways to do this. You can do it just on X. Where the output is R times X and R is a matrix. Or you can have this homogeneous matrix that has rotation in the upper left-hand corner, the 3 by 3, right? And you apply it to x1, a homogeneous version of X, right? Which is says it's, if you have Y and W, that it's the same as each one of the coordinates over W and 1. Okay? And fourth way?
Homogeneous coordinates.
Hmm?
We already talked about that, though, yeah.
Okay, there was this general axis angle thing that referred to AV. I know at least one of you, when doing the assignment, this last assignment, was confused about the difference between Quaternions, where it's also an axis angle method, and the Quaternion expresses the axis as a unit vector times sine theta over 2, and you get cosine theta over 2. So you have 4 entries here, right, where this is the axis and theta is the angle of rotation about the axis. And every rotation can be understood as the rotation about some axis by some angle, right? But it's not evident what those angles are when you just look at the rotation matrices. The rotation matrices basically say, if I have this XYZ coordinate system, what does it turn into? That's a rotation. Okay, so EX turns into the U1, and EY turns into U2, and EZ turns into U3. And so you have the matrix U1 with columns U1, U2, U3. And that is certainly a rotation, but it's not evident what the angle is. But in the lectures, we talked about how to go from that to axis angle. And the axis angle in this situation had a magnitude, which was the rotation angle, and a direction, which was the axis direction. So some were confused by this V thing and this V thing, and don't get confused, right? They're different. They're both about the axis and the angle. Well, one's about the axis only, the other is about the axis and the angle. Then unfortunately, the presentation that you were given used the letter V for both of them, right? And that was easy to easy to be confused about. Okay, but now we have 4 different ways of carrying out rotation, right? What's necessary is to have a way of carrying out rotation on points, or equivalently on vectors. Realize, of course, that a vector is simply something whose tail is at some place and whose tip is somewhere else. If the tail's at the origin and its tip is at a point, then the representation of that point, XYZ, is equivalent to the vector x times EX plus y times EY plus z times EZ. But anyway, the point is that any one of these ways is equally effective. The question of which is faster in a particular situation is dependent on what you want to do with that. So, we didn't spend time on which one of these are more efficient, but the point is that for a given job, if, for example, what you're trying to do is to interpolate between one rotation and another rotation, then you're better off using Quaternions. Well, the fact is, most of the time you're better off using Quaternions. But that doesn't say that you can't use Euler Angles if you must. Right? I don't know, does that answer your question?
Sort of. I was gonna. It was a very specific one based off last midterm, because let me see if I can find the exact question.
Okay, but the big deal that I keep harping on is that you have to understand that the basic thing that sinusoids give you is fast computation of shift invariant linear operators.
Thank you.
More questions? Yeah.
Could you go over the best kernels to use when we're finding
The what?
the best kernels to use for different bar widths? And
Okay. Kernels for bar width. So a bar is something that has strong parallel edges, the simple bar. Okay, so if you have the simplest case, you know the orientation, you know the width of the bar, and you know the bar is straight. What's the optimal kernel for finding the bar? Hmm? The Gaussian. Gaussian, the shape of the Gaussian is isotropic, right?
And the derivative in the eigenvector direction. It goes like.
Okay, derivative is a good answer, but it's not the best answer. When you want to find an object and you know exactly what the shape of the object is, what's the best kernel? The object itself. Matched filtering. Matched filters, if you know all that very specific information, then create a bar of that width and at that orientation, and run it as a kernel, right? That's the optimal one. But seldom do you have this kind of a restricted situation where you know exactly what the width is and you know exactly what the so if you have variable orientation, then the bar may be curved. And you don't know what the curvature is, right? So you can't, the match filter idea explicitly used is not available to you here, because you'd have to have match filters at every orientation. So you need something that can have variable orientation but is match filter-ish. And that's where the oriented derivative of the Gaussian, the shape that's sort of like that in cross-section, gives you something that's match filtering, because you have the possibility to provide that at lots of different orientations and figure out which is the best orientation, and you do that by using the eigenvector direction of the Hessian. Right? So that indeed, that's a very, very good answer, as long as you're in this situation where you want to be able to have different directions at different places. If you have the possibility of a narrow bar or a wide bar, and you don't know what it is, you need to be able to deal with all those bar widths, as you're interrogating the image. Say, which is the width that does that best? And then instead of the second derivative of a Gaussian at some fixed width, you need the second derivative of the Gaussian at a variety of widths, okay, which puts you in this multi-scale need. Or you can say, well, I will forego the advantage of being able to go at all sorts of orientations by using an isotropic operator that's second derivative-ish. Okay, it's not going to be as sensitive as one that can orient itself. But what is the isotropic second derivative operator? The Laplacian of the Gaussian. The Laplacian is an isotropic second derivative operator, and it will allow you essentially to have a strong response, but because it looks like the second derivative, but rotated, right? I mean, it looks like the Mexican hat. And then you can make that work, and you can make that work at many scales, but it's not as effective as if you can have your operator, your kernel, oriented in a way that matches the orientation of the bar at any place you're interested in. And then you have the fact that bars may be narrow at some places and wider at other places. And then you clearly are going to need something that is multi-scale. The spatial scale has to match at wider places. And so you're going to need to deal with that in a multi-scale arrangement like a pyramid. Does that answer your question?
Thank you.
Sure. More questions? Sure, Becca.
Can we talk about like some of the big O complexities of some of the algorithms we were expected to know for the fun?
Yeah. Okay. So first of all, I didn't really, just not being a course in algorithm analysis, I didn't carefully talk about big O and big theta. The first thing is we have the size of a target entity for an operator. So, for example, the size of an image, the number, which is the number of pixels or voxels in it. In the case of you, in this last assignment, you saw essentially tile meshes, and the number of tiles, or the number of vertices of these tiles that make up the mesh, is a measure of size. And the time to apply algorithm to an object of size m, all right, T of m. Okay? And so, for example, if m equals n squared because an image is n by n, and you have an operator that is a kernel to be applied in the space domain. So here m is n squared, and the kernel has to be applied as with weights and multiply by the weights and add them up at each kernel position. That's m squared kernel positions per pixel. There are n squared pixels. So T of m may be, in this case, m squared n squared. Yes? And there may be some other, just make up something, some other pieces of the operation that is proportional to n. Or if you do it by the frequency domain, we know that this is going to take this is for the forward FFT and the backward FFT. And then you have n squared multiplications in the frequency domain, right? For each frequency, you have to multiply by the corresponding transfer function. We have this notion, theta of m. We say T of m is theta of m. If you ignore the constant terms and you look at what happens as n gets very large, and therefore you ignore anything negligible as compared to the dominant t. And so this k2n squared is n squared times 1, and 1 grows much slower than log 2 of n as n gets very large. So this term dominates that term. So you just ignore it. And you also ignore constant terms. So only if two algorithms are theta of the same function do you care about the constant multiplier. And so we call that theta of n squared log n. Notice that I don't have to write the 2 because log a of n is a constant times log b of n. Right? The constant is, I don't know, it's either log a of b or log b of a, log base b of a. But in any case, the point is, and constant multipliers don't matter. So the point is this idea of theta means ignore constants, keep the dominant term. Okay, now you ask about O. So sometimes people write this as O of M, the set of all functions, but strictly speaking, and sometimes, well, seldom, people talk about big little O of M, but what you really want to know is theta. It turns out big O and little o have to do with including not only the ones with that dominant high term, but ones that are respectively that speed or worse, or in the other case, that speed or better. Okay? So big O has that very less specific meaning, and you probably want to use the theta notation. And that's the only one I use in the exams. Turns out theta of M is a set of all functions whose dominant term is such and so, and it's the intersection of the ones that are faster and those that are slower. So if you want to do set notation, it's the intersection of big O and little o. But that's more than you need to know for this class. By the way, the course that covers that material very, very well, first is in the data structures course, and most carefully and particularly well done is the algorithms and algorithm analysis course, Comp 550. If you ask, well, one way to characterize Comp 550, if you go for a job with a big company, you know, Apple or Google or Microsoft or anyway, they typically have an exam they give you. And pretty much all the questions on the exam are from Comp 550. It turns out it's the difference between a seriously well-educated computer scientist and one who is not that. More questions? Yeah.
Can you go over the first question on the practice final exam?
The first question on the practice final? Okay. Let me see if I can find it. I had it here. getting this question up on the screen. Let me see what I can do. That's step one. All right, that's this the one. This what you have in mind?
Yeah.
Okay. So the first thing to notice is that the Quaternion Q that's given there, cosine theta over 2 in its first slot, in its real slot, and sine theta over 2v in its second, third, and fourth slots, has a sum So V is a vector with coordinate values Vx, Vy, Vz, right? And so the size of Q is the square root of the sum of the squares of the individual entries, 4 entries. And of course, these three together are sine squared theta over 2 times v squared. But it's given that v is size 1. So this is just sine squared theta over 2, and cos squared theta over 2 plus sine squared theta over 2 is 1. So it's a unit quaternion, right? Unit quaternions do rotations, right? So this is a rotation quaternion. In general, quaternions can do rotations and uniform scaling, but this one does no scaling, only rotation. Okay? So C is true. All right? Pure rotations are about the origin. If you want it to be not about the origin, you have to do a translation of your center point to the origin, and then apply the quaternion, and then put it back. Right? So, if the rotation about the origin, you're here some distance, and a rotation puts you the same distance. That's how rotations work. So D is so. The this asks about the inverse of the quaternion. The inverse of this quaternion, let me erase some so we have room. I remind you, Q inverse just has the V. You can either think of it as V is in the opposite direction or it's sine of minus theta. Either way it's negative because the opposite angle. But the size of Q inverse is also minus sine squared and plus sine squared are just sine squared, right? So that's also a pure rotation. Yeah, an inverse of a rotation is a rotation in about the same axis, but in the opposite, by the opposite angle, by minus theta. Okay. The problem is that to rotate a point or a vector, you have to multiply by Q and Q inverse. Right? Rotation is not application of Q. If you want to rotate a vector U, you take the quaternion Q and you apply it to 0 U, which is a quaternion, and multiply that by Q inverse. And so what's wrong, the statement A is not true because it didn't talk about the multiplication by Q on the left and Q inverse on the right. That do it for you? And realize that this is either the rotation of the vector U or the point at the end of the vector if the tail is at the origin. Rotation of the point or the rotation of the vector, the same thing. More questions? A couple of administrative matters. I know y'all are concerned about your grades, and I have not been adequately careful in grading all the reports on the homeworks. They were graded automatically by the MATLAB grader, and you have those, but the reports have not been. This week I will get to that. I apologize for not having done that soon enough. If a grade appears for a homework that you think is some reason incorrect, a few of you asked for did some late submissions or otherwise. Right at the moment I have a note to myself that I think it was assignment 6, but I haven't yet gone back and looked at it for Junier and for Madison and from Emma. But I will. I haven't forgotten. But anyway, we're required to get grades in 72 hours from the end of the exam. So the exam is due on Tuesday, next Tuesday, yes? a week from today. And so by the end of that work week, I'm supposed to get the grades in. That Wednesday is a very full day for me. I won't be doing any grading on Wednesday. We're going to be putting together grades on Thursday. If you feel that the grading of the exam or grading of some homeworks were not fairly done, please get your concerns to me by noon on that Thursday, or well, by that Thursday sometime, right? Because by Friday I'm going to have to submit the grades. What normally has happened for people who've done all the assignments is they have a quite good assignments grade and a bit lower exam score. Remember that if you do better on the final than you did on the midterm, the midterm grade will be ignored. And if you do worse, then the final and the midterm will be averaged to give you your exam score. But anyway, what can I say? I'm first and foremost in the business of teaching you the content of the course, and for various reasons grades are required, and so it's motivation for you all and a way for the university various people in the university to evaluate you, and so we have to do the grades. And I want to be completely fair with you. So please don't worry about, he's going to see me as a grade grubber. No, if you feel like I'm not evaluating you in a fair way, please let me know. But let me know before I have to insert the grades, since it's really, really complicated to change a grade after the grades are submitted. There are few grad students in the course. They'll get grades in the HPLF type of scale, and of course undergraduates will get A's and B's and C's and so on, and pluses and minuses. Just to let you know how things go, next Wednesday at 11 in I believe in room 011 Sitterson, but also on Zoom is the dissertation defense of one of my dissertation advisees. His name is Jurian Liu, and it's a dissertation on methods for representing objects with target problems of structures in the brain, and in diagnosis of, target problem autism on the basis of the shape of brain structures. And if you're interested in that, defenses are open to the public. You are most cordially invited, either by Zoom or by attendance in person. And if you want the Zoom site, send me an email and I'll be happy to share that with you. The other thing that happens on that very same day, at computer science, the qualifying exam process involves early grad students having done research for a year and a half or so, for 3 semesters, and write a paper, and then there is an examination process, not by the advisor of the research, but by 3 other professors. and those are called preliminary research paper exams, PRP. And those are one-by-one presentations by students, and they take place in FB 142, and those presentations are also open to the public. And there are a couple of them that are on medical image computing topics that you might be interested in, given that. And again, you're welcome to those. The way that goes is there's a 25-minute presentation, and then questions open to anybody, to the public, to anybody who's attending, and then questions in public by the examining committee, and then a private opportunity for a few more questions by the examining committee. You're not, of course, welcome in the private part, but the public part, you're most cordially invited.
What room did you say it was in again?
FB 142. It's sort of, the door is sort of, it's on the south end. Well, we're in FB 107, right? If you walk out here and turn left, there's a cross corridor. We're in FB 007, I guess, huh?
It's wonderful.
One floor up, and sort of the middle door
Thank you.
there. It's so-called faculty conference room, I think. Okay, so for those of you who are studying and want to ask further questions, I'll be here 9:30 on Thursday. And again, I'll be in my office 3:30 on Friday. And I I know that you've learned a good deal in this course. I hope you find it useful going forward. I've enjoyed teaching you. Bye-bye.
Thank you, sir.
You're welcome.